up to 1 plus 3 plus 5 plus data all the way to 2k minus 1. Just plug in n equal to k. And that means on the left hand side means the sum of the first k odd numbers. And this will be equal to k squared. I assume this is true, okay? And we try to prove that. So we need to prove that the equation is also true for n equal to k plus 1. So if it's true for k, it will be true for k plus 1. Alright? And by the way, this is the step Pn right here. P1, P2, this is really P2, P3, P4, P5, the statement. P stands for any logical statement, right? P1 is statement with n equal to 1, P2 is n equal to 2, P3, n equal to 3, so forth and so on. So we assume to keep it through until Pk is still true. Alright? And we need to show that what? If Pk is true, then Pk plus 1 will be true for sure. Which means what? 1 plus 3 plus 5 plus all the way to 2 times k plus 1 minus 1. You guys see how I write it right here? N equal to k plus 1, right? So what? I plug in n equal to k plus 1. And this really means what? The sum of the first k plus 1 odd numbers. So this is the sum of k odd numbers. N is k. Then with n equal to k plus 1 is the sum of n plus 1 k odd numbers. It's going to be equal to k plus 1 squared because now n equal to k plus 1. We don't have it yet. We try to prove this thing going to happen. Okay? So how do we prove this? As I mentioned before, we will always need to use the assumption that we have. And by the way, this is really p of k plus 1. Alright? And again, this is the sum of k plus 1 odd number. And what do we mean by that? It's going to be equal to the sum of the first k odd numbers and then plus the last number. This means 1 plus 3 plus 5 plus data all the way to 2k minus 1 and then plus the last number 2 times k plus 1 minus 1. Think of k as counting 1, 2, 3, 4, 5 all the way to k and then k plus 1. Okay? And why do we need that? Because this is the sum of the first k terms. So we can use the assumption step right here. And the sum of the first k odd numbers will be equal to k squared. That's what we have. And hopefully, k squared plus, we're going to simplify this a little, right? So 2k plus 2 minus 1 will be equal to k plus 1 squared. And this is k squared plus 2k plus 1. I combine the like terms. That's really equal to k plus 1 squared. So that's true, right? So what we're saying here is what? The first steps, the first couple steps are true. And we assume it's true to k, then for sure it will be true for k plus 1. And with that logic, if true for k plus 1, for sure k plus 2 will true, k plus 2 will true for k plus 4, k plus 3, and plus 4, plus 5. And true forever. So you have to write a conclusion. Say what? Therefore, by math induction, the equation is true for all n. Okay? Now what's the idea? Let me, this is pretty much the same for all problems, so let me just give you one more example of this type, and hopefully that will be clear enough. Just practice, okay? The hardest part is right here. You need to use your math skills to use the assumption of pk to prove that pk plus 1 is true, okay? This is the most important step for math induction. Now let me look at another example. All right, and I found one. Let's prove that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus all the way to 1 over n times n plus 1 will be equal to n over n plus 1. So what you see in here, the left-hand side is the sum of a bunch of fractions, right? The numerator is always equal to 1. Denominator is a product of two consecutive numbers, 1 times 2, then 2 times 3, 3 times 4. You can guess the next one is going to be 4 times 5, 5 times 6, so forth and so on, until the n is n times n plus 1. So pretty much this here, on the left-hand side is the sum of n fractions of this type will be equal to n over n plus 1. So how do you prove that this equation is always true for all n? Again, with this type of problem, math induction would be the best method to take care of the problem. So the first step, you're going to test for n equal to 1. Was that really true? N equal to 1 means on the left-hand side you only have one fraction, 1 over 1 times 2. Is that equal to 1 over 1 plus 1? I'm looking at n equal to 1, right? On the left-hand side, one fraction. Right-hand side, 1 over 1 plus 1. Equal to 1/2. Awesome. It's good. And if you think it's not enough, you can check for more, but I claim this is enough. And again, lecture. So I'm going to test for one more, okay? Say this is really P1. Was that really true when n equal to 2? What do I have? Left-hand side is 1 over 1 times 2 plus 1 over 2 times 3. Because on the left-hand side, number n come up all the way to 2, right? So what? The first term is 1 over 1 times 2, and then n equal to 2 is 1 over 2 times 3. So what? 2 fractions. And hopefully this will be equal to 2 over 2 plus 1. Look, this is 1/2 plus this one is what? 1 over 6. So this is really 3 over 6 plus 1 over 6, which is 4 over 6, which is 2/3. Awesome, it's true. And as you see, when n equal to 2 is true, I'm pretty sure to say that. When n equal to 3, n equal to 4, n equal to 5 is all true. So we're going to move on to the assumption step. Okay. Assume that the equation is true for n equal to k, which means 1 over 1 times 2 plus 1 over 2 times 3 plus da all the way to 1 over k times k plus 1 will be equal to k over k plus 1. All right? So this step is really pk right here. We show that. We assume that, okay? We are assuming that the sum of the first k fractions of this type will be equal to k over k plus 1. Then we need to prove that. The equation is also true for n equal to k plus 1. So if it's k for the sum of k fraction, it'll be true for sum of k plus 1 fraction. We have to prove it. We don't have it yet. Okay? So that means 1 over 1 times 2 plus 1 over 2 times 3 plus and then plus 1 over k plus 1 times k plus 2. And this is the sum of k plus 1 fractions. Hopefully it will be equal to k plus 1 over k plus 2. You see? This is k over k plus 1, right? So the next step will be k plus 1 over k plus 2. Plus 2. All right. So how do we prove that? This is the sum of k plus 1 fraction. As usual, it's equal to the sum of k fraction and then plus the last one. I already have room, so I'm going to write it here on the left hand side. On the right hand side. 1 over 1 times 2 plus 1 over 2 times 3 plus The last term is 1 over k plus 1 times k plus 2. So the previous fraction will be 1 over k times k plus 1. Okay? And hopefully it's equal to k plus 1 over k plus 2. We hope that happens. We don't have it yet. We'll try to prove. And as I said before, always use the assumption here. The sum of the first k fraction always equal to what? K over k plus 1, right? And then you add 1 over k plus 1. This is k plus 2, I think. Times k plus 2. Hopefully it's equal to k plus 1 over k plus 2. So how do you add fractions? You're going to make the common denominator. So multiply the first fraction by k plus 2. K plus 2. So we have what? K squared plus 2k plus 1. I simplify distribution, k squared 2k, and then plus 1 right here over k plus 1 times k plus 2, right? And then I factor the top out, we got k plus 1 times k plus 1 over k plus 1 times k plus 2. Of course, k plus 1 cancel out. Go to k plus 1 over k plus 2, you see? And you can say, give conclusion, say what? By math induction, this equation will be true for all n. Okay? And I will stop this video clip, cover the section of math induction right here. Hopefully, via a couple of examples, has helped you to understand the idea, the concept of math induction. And please spend some time in practice. If you have any question, please let me know. Thank you and have a good day, guys.